Hey everyone, today we'll be solving this question Xor-Distance that came in Codeforces round 922 div 2. In this question, you'll be given three integers a, b, r, and you need to find the smallest value of the absolute difference between a Xor x and b Xor x, and x should be in between 0 to r. So let me show this in a detailed way.
In the question, you will be given with ABR, and you need to minimize the difference between A XOR X and B XOR X. And X should be less than equals to R, greater than equals to 0. The constraints that given in the question for R is up to 10 to the power 18. Now, if you want to go iteratively for each and every R from 1 to R and calculating that is it a possible X to minimize R and so, then it would take 10 to the power 18 big of, and it would be a time we can exceed solution. But we can go in the binary form because it would range up to 2 to the power 60, and we'll be calculating for 60 bits, and that is possible for sure. Now let's say we are having AB and I want to check for the ith position whether to put a 0 or 1. How can I check that? If the bit at ith position for A as well as for B are same, then do nothing. Why? Because I want to minimize the difference. If AI, let's say xi minus bi xi, if AI is 1 and xi is 0, it would be 0. So we can have 0 at that position, at that bit position for our answer, and that we want to minimize our answer. So if they are equal, and by subtracting they'll get cancelled out, and we'll have a 0 in that position for our answer. Now if they are not same, what to put? Either 1 or 0. So this thing we need to calculate. Let me take an example. Let's say A is 1, B is 14, and R is 5. In the binary form we can write it as this. For A it would be 0001. That is the first term, A XOR X. Second term, that is A XOR X, and that is our actual X. Now the bit position 0, 1, 2, 3. Now if I'm checking for the third bit position, they are different. Now what to put in our X? It would be 2 to the 3 if I want to put a 1 in our X, and that will be 8. 8 is greater than R, so we can't put 1 in that bit position. So our first term over here would be 1, and for second term it would be 0. Now again in the second bit position these bits are different. That would cost up to 2 to the power 2 for R, and it is lesser than R. Then I can change this to either 1 or 0. So I'm putting a question mark over here. I'll decide this later on. So same for this, they are different. I can put anything. As 2 to the power 2 is less than R, then 2 to the power 1 as well as 2 to the power 0 will also be lesser than R. Now I need to check for these positions for X as well as for S and F. There is a first term and second term. Now I'm checking for the other bit position that I have calculated. We can clearly see F would be definitely big greater, even if like S, F is this. Now S is this. Even if I put 1 to the other position for S and 0 to the other position for F, even though F would be greater than S, if F is greater than S, then it will remain that only, because the other bit positions are lesser than which already have been set. So I want to maximize s to minimize our answer, because f is already greater than s, so I want to increase s so it goes closer to f and our answer will be minimized. Now I want to put a 1 if possible. I'll give priority to the higher bit position, because we know that 2 to the 2 is definitely greater than, like, 100 is greater than 11011. So I'll give preference to the higher bits to maximize my s. So 2 to the 2 is less than r. Yes, I can put a 1 over here in our x, but our r will get reduced to 5 minus 4. It would be now 1. R would be now 1. That is 5 minus 4, 1. Now, can I put a 1 over here again? To put a 1, I want a 1 in my x. Is it possible? That would cost up to 2 to the power 2. And that would cost up to 2 to the power of 1. And it's not possible. So I'll be putting a 0 over here only. And this will be a 0. And this will be a 1. Now, can I put a 1 in our s over here? For this, I want a 0 in my x. Yeah, putting a 0 is possible. And in our f, it would be a 0. So this is my second term and this is my first term. Now I'll be calculating the difference between them, and it would be 5 only. That is, this is 10 and this is 5. So 10 minus 5 is 5. So that's our answer. So the basic idea is, if both are equal, then let's say I have the best to be assigned. It's the fourth position, third position, second position, and the first position. This are needs to be decided what to put on. And if and s are equal, then what could I do? I can assign the first bit favorable to f or s anything, and the other bits favorable to s or s and f. So the minimum would be our answer. I'll assign the first bit favorable to any one of the term and the other bits favorable to other term. If f is less than s, then for sure I need to increase my f to minimize the difference between f and s. So all the bits I'll try to be favorable for f. If f is greater than s, then I'll try to maximize s. And so all the bits which I haven't decided yet, so this bits I'll try to be favorable for s. So that's the intuition. Let me show the code, it will be more clear. In this code, I have first taken a position array and then initialized this with 0. Now I'm moving from 60th position to 0 position. Temp is to check that at the ith position A has 1 or 0. Either of them are same or not. Both are same, it means A and B at the ith position have same bit. So we don't have to do anything if both the bits are same at the ith position, because they will get eliminated when we are subtracting. Now, if temp is R, it means that I cannot put 1 at the ith position in our x. So I'm checking that what my first term would be if x at ith position has 0. So temp and a is greater than 0, it means a has 1 at the ith bit position. That's why I'm doing or with 1 at the ith position for the first term. Else it means this b has 1 at the ith position. So I'm doing a or with s, so that s would have 1 at the ith position. Else it means temp is less than equals to r, so I can have 1 at the ith position. So I'm putting position of I as 1. That I'll check later on. Now I'll be checking that first and second term, if they are same, then I need to assign the first bit, like the first bit from the 60th bit position, that the last bit that I could change to 1, I'll assign that to f or s. So I'm taking the minimum of them. Let me show the find function in which I have taken a, b, fs, and r.
This is checking that the first bit I'll assign to F, that is favorable to F, and all the other bits to S. And the second one is checking that I'll be assigning the first bit favorable to the second term and the other bits favorable to the first term. Let me show that. So I'm going from the 60th position. So I need to assign the first bit to F now. So if it is 1, then I'll simply do a odd operation with F. Now I have to check A has 1 or not at the ith position. If it is 0, it means A has 0 at the ith position. So I have to have 1 at X on the ith position. So that's why R need to be reduced, because I am assigning X with 1 at the ith position. So that cost up to 2 to the power of I. That's why I'm reducing our R. Now I'm doing I minus minus and break, because I will be assigning only one bit to the first term and the other bit to the second term. Now I'm assigning all the other bits favorable to the second term. That if it is 1, then I can assign 1. Now I'm checking, does B have 1 at the ith position or not? If it doesn't have, then I need to check that 2 to the power of I is less than equals to R or not. If it is, then only I can have that, because I have a condition to less than equals to R. That's why I'm doing a OR with 1. That is 2 to the power of I. Now I'm reducing our R. If we don't have R greater than equals to 2 to the power I, then I have to assign 1 at the ith position to F only. That is the first term, because I cannot go for 1 in the second term, because we don't have enough R. Now, if we already have at the ith position as 1, then I'm assigning or with S at the ith position, that we can put a 0 in our X, because we already have 1 and that we want. So that's it. And after that, I'm returning the difference between F and S. If both are same, I'm checking that. But if F is greater than S, then I need to increase the second term by assigning all the other bits that is possible. So I'm checking for all the other bits from the last bit position from the 60 to 0. So if it is 1, it means I can assign 1. So that's why I'm checking that B already have 1 or not. If it already have, then I'll be having 0 at the ith position for X, and that doesn't cost anything. So I'm just doing a OR with 2 to the I. But if B doesn't have, then we need to pay a cost of 2 to the I. So I'm reducing that from R and doing a OR with S. But if we don't have enough R, then we have to give this 1 to the first bit only. And again, I'm in decrementing the I, and answer would be the absolute difference between F and S. But what if S is greater than F? Then I have to increase F. So I'm doing the same thing for F now, that incrementing the F if possible from the last position to the 0th position, and again the absolute difference would be our answer, and then printing it. So the basic idea is, if both are equal, then I'm checking for either to put for F or S and taking the minimum of both. If F is greater than S, then increment S. If F is less than S, then increment F. That's it. I hope you like it. Thank you for watching.